planets. This planet, with its relentless winds and scorching heat, is one of the many nightmares we've uncovered in the cosmos, a place where life as we know it could never exist. But even as we map these alien hellscapes, we are driven by a hopeful question. If such hostile worlds can exist, might there also be paradises hidden among the stars? The search for a second Earth continues, fueled by discoveries that challenge our understanding of planets, their formation, and the conditions necessary for life. If you find this video helpful, please give us a subscribe. A small compliment from you is a huge motivation for us. The hunt for exoplanets, planets beyond our solar system, has revealed an astonishing diversity of worlds. Some are gas giants orbiting dangerously close to their stars, scorched and swollen by extreme radiation. Others are rocky planets shrouded in toxic atmospheres, or frozen in perpetual darkness far from their parent stars. These discoveries have shattered the notion that most planetary systems would mirror our own. Instead, the universe seems to favor chaos and extremes. Consider another example. Kepler 10b, a rocky planet discovered by the Kepler Space Telescope. It is so close to its star that temperatures soar to over 2,500 degrees Fahrenheit, hot enough to melt iron. Its surface, if it exists at all, is likely a molten sea of lava. Kepler 10b is a place of extremes, orbiting its star once every 20 hours. For comparison, Mercury, the closest planet to our Sun, takes 88 days to complete its orbit. Such close proximity to a star is a recipe for destruction, leaving no room for life to take hold. Then there are the so-called hot Jupiters, massive gas giants that defy expectations. Unlike the cool, distant Jupiter in our solar system, these planets orbit perilously close to their stars, where searing temperatures and intense gravitational forces twist and warp their atmospheres. The heat from their stars causes these giants to swell to enormous sizes, their outer layers of gas slowly being stripped away into space. WASP 12b, for instance, is being consumed by its star, leaving behind a trail of gas like the ghost of a comet. While such planets seem utterly alien, each discovery provides valuable insights into the mechanics of planetary systems. They show us the extremes of nature, the outer boundaries of what a planet can endure. And yet, even in these hostile environments, we learn more about the possibilities for planets to exist in stable, life-supporting conditions. The search for a habitable world continues with super-Earths, rocky planets larger than Earth, but smaller than gas giants like Neptune. These planets exist in a tantalizing category, big enough to hold on to thick atmospheres and potentially liquid water, but not so large as to become inhospitable gas worlds. Super-Earths are particularly intriguing because they seem more common than Earth-sized planets, offering a wider canvas for life to emerge. One of the most promising candidates is Proxima Centauri b, a planet orbiting the closest star to our solar system. Located just over 4 light-years away, Proxima Centauri b resides in its star's habitable zone, the region where conditions might allow liquid water to exist. However, its parent star is a red dwarf, prone to violent solar flares that could strip away the planet's atmosphere and make life difficult. Despite this, its proximity makes it an exciting target for future missions that could study its atmosphere and surface. Another intriguing discovery is the TRAPPIST-1 system. home to 7 Earth-sized planets, 3 of which orbit within the habitable zone. This system offers a rare glimpse into a tightly packed planetary neighborhood, where gravitational interactions between planets may play a critical role in their potential to support life. Could one of these worlds be the paradise we seek? Even as we find more planets that seem hostile to life, the search for a second Earth presses on. With tools like the James Webb Space Telescope, capable of analyzing the atmospheres of distant exoplanets, we are on the brink of understanding whether these planets harbor the right conditions for life. Webb's ability to detect signs of water vapor, carbon dioxide, methane, and even oxygen in exoplanet atmospheres will be revolutionary. Such biosignatures could be the first hints of alien life. Our journey is far from over. The universe, vast and brimming with possibilities, holds untold secrets. The more we explore, the more we realize how unique and fragile our own pale blue dot truly is. The search for another Earth is not just a quest to find life elsewhere. It is a reflection of our desire to understand our place in the cosmos. Somewhere out there, a world like ours may exist, orbiting a distant star, waiting to be discovered. For now, we continue to gaze at the heavens, driven by hope, curiosity, and the enduring question: are we alone? The discovery of WASP-12b, a world transformed from a cold gas giant into a blazing inferno, reveals the dramatic forces at play in the cosmos. This planet's journey from the frigid outer reaches of its star system to the fiery embrace of its parent star is a testament to the power of gravity and the chaotic nature of planetary formation. WASP-12b is a galactic pioneer, showing us how the universe can sculpt seemingly impossible worlds. But WASP-12b isn't alone in its fiery fate. Hot Jupiters like it challenge our understanding of how planetary systems form and evolve. These gas giants start far from their stars, in the icy depths where their massive atmospheres can coalesce. Over time, they migrate inward, pulled by the gravitational forces of the swirling disk of gas and dust from which they were born. This inward migration is a slow but inevitable journey, stretching over hundreds of thousands or even millions of years. By the time a planet like WASP-12b reaches its final orbit, it has been utterly transformed. Close to its star, a gas giant faces relentless forces. The heat puffs up its atmosphere, stripping away layers of gas in a process that can eventually destroy the planet altogether. For WASP-12b, this destruction is already underway. Its star is ripping away nearly 190 quadrillion tons of gas every year, creating a glowing tail of material stretching into space. In just 10 million years, a blink in cosmic terms, WASP-12bi will cease to exist, consumed by its star. What makes WASP-12b even more fascinating is the nature of its core. Beneath its inflated, styrofoam-like atmosphere lies a solid heart rich in carbon. The immense pressures at this depth could compress carbon into exotic forms, potentially creating mountains of diamonds and vast seas of liquid tar. WASP-12b, like so many hot Jupiters, is a world of extremes, a volatile cocktail of fire, gas, and unimaginable pressures. These insights force us to rethink the diversity of planets in the galaxy. WASP-12b is a vivid reminder that not all planetary systems resemble our own. While we marvel at the stability and relative calm of our solar system, it is an outlier in the grand scheme of the universe. The cosmos is full of chaotic, violent, and inhospitable worlds, many of which stretch the boundaries of what we thought possible. Consider the case of Kepler 70b, one of the most extreme planets ever discovered. This rocky world orbits so close to its parent star that it completes a full orbit in just 8 hours. The temperatures on its surface exceed 12,000 degrees Fahrenheit, hotter than some stars. Kepler 70b was once a gas giant, but as its star aged and expanded, the planet was stripped of its outer layers, leaving behind a molten core that continues to bake under the intense heat. It is, quite literally, a planet on fire, a burning ember orbiting a dying star. The discovery of such worlds forces us to confront an unsettling question. How many of these planets were once habitable? Could some of them have started as lush, water-rich worlds before spiraling into the deadly embrace of their stars? The violent forces that shape planets like WASP-12b and Kepler 70b remind us that planetary stability is not guaranteed. Even Earth's orbit could theoretically change under the influence of gravitational interactions over billions of years. Not all migrating planets become hot Jupiters or fiery wastelands. Some are flung entirely out of their star systems. These rogue planets, untethered to any star, drift through the galaxy in perpetual darkness. Without a parent star to provide light and warmth, rogue planets are among the most inhospitable places in the universe. Yet, some scientists speculate that if a rogue planet retains a thick atmosphere or a subsurface ocean, it might still harbor life, warmed by the planet's internal heat. The story of planetary migration extends beyond hot Jupiters and rogue worlds. It also offers clues to the formation of solar systems like our own. In our solar system, gas giants like Jupiter and Saturn likely migrated slightly inward during their formation, shaping the orbits of smaller planets like Earth. Without this delicate balancing act, the stable, life-supporting environment of our planet might never have existed. The process of planetary migration highlights the dynamic nature of the universe. Stars, planets, and moons are not static. They evolve and interact in ways that continually reshape their environments. This dynamism is both a source of destruction and a catalyst for creation. Planets collide, stars explode, and galaxies merge, creating new worlds in their wake. As we continue to search the galaxy for Earth-like planets, the diversity of exoplanets reminds us of the fragility and uniqueness of our own world. For every potential paradise, we find countless hellish landscapes where life as we know it could never survive. Yet, these discoveries fuel our curiosity and expand our understanding of what is possible in the cosmos. WASP-12b and its kin, though inhospitable, serve as cosmic laboratories. They help us understand the forces that shape planets, the extremes of atmospheric chemistry, and the resilience of matter in the face of extreme conditions. Each discovery brings us closer to answering the ultimate question: are we alone? Somewhere in the galaxy, there may be a planet that mirrors our own, a pale blue dot with the right conditions for life. Until we find it, the hellish worlds like WASP-12b remind us of the wonders and challenges of the universe, urging us to continue our exploration of the stars. Korot 7b, a world caught between extremes, reveals the violent and unpredictable nature of the universe. This once massive gas giant, 100 times the size of Earth, has been reduced to a hellish shadow of its former self. Its journey from a cold, gaseous world to a rocky planet of fire and ice is a chilling reminder of the power of gravity and the destructive forces at play in planetary systems. 1.5 billion years ago, Corot 7b began its life far from its star, wrapped in thick layers of gas and ice. Like other gas giants, it formed in the cold outer regions of its star system, where gravity gathered dust and gas into a colossal planet. For millions of years, it remained in this stable, frozen orbit. But then, something changed. A larger, more massive planet began to disrupt the delicate balance of the system, a hot Jupiter moving inexorably toward the star. As the hot Jupiter spiraled inward, its immense gravity began to wreak havoc. Smaller planets were flung into chaotic orbits, and Corot 7b was dragged closer and closer to its star. The once frigid world entered a scorching, unforgiving environment. The heat stripped away its gaseous envelope, layer by layer, until all that remained was its rocky core. What was left behind is a planet of extremes, one that defies the imagination. Today, Corot 7b is locked in a tidal embrace with its star, its rotation synchronized so that one side always faces the heat, while the other is plunged into eternal darkness. The side facing the star is an inferno. Temperatures exceed 4,700 degrees Fahrenheit, hot enough to vaporize rock. The atmosphere, if it can be called that, is a swirling mix of vaporized minerals. Winds carry this molten material to cooler regions, where it condenses into pebbles and rains down, literally a rain of rocks. It's a scene that seems pulled straight from the depths of mythology, a planet where the sky itself burns and solid stone falls like hail. Move to the planet's twilight zone, and the extremes ease slightly. Here, the heat of the star gives way to a narrow band of cooler temperatures. Lava flows cool and solidify into rocky plains. It is a brief respite in an otherwise brutal landscape, but this temperate region is razor thin, a sliver of potential calm surrounded by chaos. Beyond it lies the dark side of the planet. On this far side, the absence of the star's warmth creates a realm of unrelenting cold. Temperatures plummet to hundreds of degrees below zero, freezing everything into an icy stillness. It is a stark contrast to the molten hell of the dayside, yet just as hostile to life. This is a planet of fire and ice, a place where the extremes of temperature make survival impossible. Corot 7b's story is not unique. It is one of many rocky worlds we've discovered, each shaped by violent forces. These planets reveal how far the universe is from the hospitable environments we see on Earth. Rocky exoplanets like 55 Cancri E, for instance, share similarities with Corot 7b. This world, 8 times the mass of Earth, orbits its star at such close range that its year lasts just 18 hours. Its surface is also an inferno, covered in lava flows and scorched by relentless heat. These worlds remind us that Earth is a rare oasis in a universe dominated by extremes. But Corot 7b and its kin are not the only planetary nightmares out there. The chaos wrought by migrating hot Jupiters extends far beyond the planets they drag toward their stars. These massive gas giants also destabilize their star systems, flinging smaller planets into wildly eccentric orbits, or ejecting them entirely into interstellar space. These are the rogue planets, orphan worlds cast adrift between the stars. Rogue planets are enigmatic and haunting. Without a star to orbit, they travel through the darkness of space, illuminated only by distant starlight. On the surface of a rogue planet, the night sky would be unchanging and eerily silent. There would be no sunrise or sunset, no warmth to sustain life. These planets, severed from their parent stars, are relics of violent gravitational battles. Some were gas giants like Coro 7b, while others might be rocky worlds, frozen Earth-like planets cast into perpetual night. What makes rogue planets even more astonishing is their sheer number. Some estimates suggest that these orphan worlds may outnumber stars in the galaxy. If true, it would mean hundreds of billions of planets roam the void between the stars, their stories lost to the darkness. Despite their isolation, rogue planets may still hold secrets. If a rocky rogue planet retains a thick atmosphere or subsurface ocean, it could generate heat through radioactive decay or tidal forces. In such cases, even these dark, frozen worlds could harbor life in some form. A tantalizing possibility that challenges our understanding of what makes a planet habitable. The story of Coro 7b, rogue planets, and hot Jupiters underscores the unpredictability of planetary formation and evolution. While we search for Earth-like worlds, the reality is that most planets are profoundly different from our own. They are shaped by chaos and violence, molded by forces that destroy as much as they create. Yet, these discoveries also remind us of Earth's uniqueness. In a galaxy filled with planets of fire and ice, rogue wanderers and searing giants, our pale blue dot remains a rare and fragile gem. The search for other worlds continues, but each step reveals just how extraordinary our own world truly is. As we gaze out into the cosmos, these planets from hell inspire awe and caution. They show us the extremes of the universe and remind us of the delicate balance that makes Earth so special. Somewhere, perhaps, another world like ours may exist, a haven of life in an otherwise hostile galaxy. Until we find it, we will continue to explore, learn, and marvel at the diversity of the universe. The discoveries made by NASA's Kepler Space Telescope have revolutionized our understanding of the cosmos. Kepler has revealed a galaxy teeming with planets, planets of all sizes, compositions, and orbital paths. Among them, some are fiery infernos, others frozen wastelands, and a select few hold the tantalizing promise of being just right. This sheer abundance of planets is both humbling and hopeful. While most of the worlds we've found are utterly inhospitable, their sheer number suggests that habitable planets like Earth might not be as rare as they seem. The key to finding another Earth lies in identifying planets located within the Goldilocks zone, the region around a star where conditions are just right for liquid water to exist. Water is fundamental to life as we know it, acting as the universal solvent where complex chemistry can flourish. Without water, there can be no oceans, no rivers, no rain, and likely no life. As astronomers often say, follow the water. It's the guiding principle for our search. Kepler allows us to pinpoint a planet's distance from its star, a critical factor in determining habitability. Too close, and water boils away into vapor, leaving behind barren deserts. Too far, and water freezes into perpetual ice, locking a planet in a frozen state. Earth exists in the sweet spot, a precarious balance that has allowed life to thrive. Finding planets with a similar balance is the ultimate goal of planet hunters. But the search has been anything but straightforward. Kepler has identified thousands of planetary candidates, but few lie within their star's habitable zone. And none so far have been confirmed as true Earth twins. Instead, we've uncovered a kaleidoscope of alien worlds that push the boundaries of what planets can be. Coro 7b, with its rain of molten rock, and pulsar planets, bombarded by deadly radiation, are stark reminders of the universe's extremes. These are worlds where the concept of life seems impossible, where even the barest conditions for survival are absent. Yet, the sheer number of planets we've found is reason for optimism. Planets, it seems, are easy to make. The galaxy is brimming with them. 50 billion by some estimates, with many orbiting stars like our Sun. If planets are so abundant, then even the rarest ones, those that resemble Earth, could exist in significant numbers. Statistically, there must be other planets out there with conditions similar to ours. Consider the potential implications. Even if only 1% of planets are in the Goldilocks zone, that could still mean 500 million potentially habitable planets in the Milky Way alone. The vastness of these numbers inspires hope, even as it challenges our imagination. Among the countless stars and their orbiting planets, there may be dozens, hundreds, or even thousands of Earth-like worlds waiting to be discovered. Kepler's discoveries have also deepened our appreciation for Earth's uniqueness. Our planet is not only in the perfect location relative to the Sun, but it also benefits from a host of other factors that make life possible. Its magnetic field shields us from harmful radiation, its atmosphere retains heat and provides oxygen, and its stable climate supports diverse ecosystems. Together, these factors create a delicate balance that might be exceedingly rare in the cosmos. As we continue to search for Earth's twin, new technologies promise to bring us closer to an answer. The James Webb Space Telescope, for example, is designed to analyze the atmospheres of distant exoplanets, searching for signs of habitability or even life. By detecting the presence of water vapor, oxygen, methane, and other biosignatures, Webb could provide the first concrete evidence of planets capable of supporting life. Even beyond James Webb, upcoming missions like TESS, Transiting Exoplanet Survey Satellite, and the European Space Agency's PLATO mission are expected to expand our catalog of exoplanets. With each new discovery, we refine our understanding of where and how to look for habitable worlds. These tools bring us closer to answering the age-old question: are we alone? The search for exoplanets is not just about finding life elsewhere. It's about understanding our place in the universe. Each new planet we discover, whether a fiery gas giant or a frozen rogue world, adds to our knowledge of how planetary systems form and evolve. They remind us of the diversity of the cosmos and the fragile conditions that make Earth so special. Despite the challenges, the search continues with undiminished fervor. For every planet from hell we uncover, we gain insights into the mechanisms that create and sustain planets. For every failed attempt to find an Earth twin, we are reminded of the vast possibilities that lie ahead. Somewhere in the galaxy, orbiting a distant star, there may be a pale blue dot just like ours. A world teeming with life, oceans, and skies, waiting to be found. Until that day comes, our journey among the stars serves as a testament to humanity's curiosity and determination to explore the unknown. Kepler has opened our eyes to a universe full of planets. It has shown us the extremes, the inhospitable, and the breathtakingly alien. But it has also given us hope, a belief that among the billions of planets in our galaxy, there are worlds that could be home to life, worlds that might one day answer the profound question: are we alone? Hubble's discovery was revolutionary, but it also raised profound questions. If the universe had a beginning, what triggered it? What existed before the universe began? These questions have intrigued and challenged scientists for nearly a century, driving deeper exploration into the origins of everything we see today. To understand the birth of the cosmos is to understand the origins of ourselves. The Big Bang. The story begins with the Big Bang, an unimaginably violent event that occurred approximately 13.8 billion years ago. In an instant, an infinitely dense and hot singularity expanded, creating space, time, and all the energy that would ever exist. The universe was born in a flash of light and heat, a tiny speck of incredible energy that began expanding at an unimaginable rate. This was no ordinary explosion. It was an expansion of space itself, stretching the fabric of the cosmos and setting the stage for everything that would follow. During the first fractions of a second, the universe was a seething sea of energy. Temperatures were so high that matter as we know it could not exist. Instead, the universe was filled with fundamental particles like quarks and gluons, zipping around in chaotic motion. These particles were the building blocks of the atoms that would eventually make up stars, planets, and life itself. But first, the universe had to cool. As the universe expanded, it began to cool down. Within minutes of the Big Bang, quarks combined to form protons and neutrons, creating the nuclei of the first atoms, mostly hydrogen and helium. These two elements are the simplest and most abundant in the universe, and they remain its primary constituents even today. The next step in the cosmic story would take hundreds of millions of years. As the universe continued to cool and expand, gravity began to take hold. Hydrogen and helium gas clouds coalesced under the pull of gravity, forming the first stars. These stars were massive, burning their fuel at extraordinary rates and exploding as supernovae after just a few million years. These violent explosions seeded the universe with heavier elements like carbon, oxygen, and iron, the building blocks of planets, life, and everything we see around us. Stars, it turns out, are the universe's factories. Inside their cores, nuclear fusion forges heavier elements from lighter ones. For instance, hydrogen atoms combine to form helium. And in larger stars, helium atoms fuse to create carbon, oxygen, and eventually iron. When these stars die, they scatter these elements into space, enriching the universe with the raw materials for new stars, planets, and eventually life. Physicist Lawrence Krauss explains it best. We are truly stardust. The atoms in our bodies were forged in the cores of stars that lived and died billions of years ago. Every breath we take, every step we make, connects us to the cosmos in the most profound way. The iron in your blood, the calcium in your bones, the carbon in your DNA, all of it was born in the hearts of stars that lived and died long before our sun ever existed. The formation of the first galaxies was the next major milestone in the universe's evolution. Over hundreds of millions of years, gravity pulled clumps of stars together, creating swirling islands of light. Galaxies. These vast star cities are the building blocks of the cosmos, each containing billions or even trillions of stars. Galaxies, like stars, come in many shapes and sizes. Some are elegant spirals, like our own Milky Way, while others are chaotic and irregular, shaped by collisions and interactions with neighboring galaxies. The formation of our solar system occurred much later. about 4.6 billion years ago. It began with a massive cloud of gas and dust, which collapsed under gravity to form a new star, our Sun. Around the Sun, smaller clumps of material collided and merged, forming the planets, moons, asteroids, and comets we see today. Earth, our home, was one of these rocky worlds, forming in the Sun's habitable zone, where conditions were just right for liquid water to exist. The young Earth was a fiery, hostile place, bombarded by asteroids and volcanic eruptions. Yet, from this chaos emerged the conditions necessary for life. Over billions of years, the planet cooled, oceans formed, and primitive life took hold. From simple microorganisms, life on Earth evolved into the incredible diversity we see today, a process spanning billions of years and shaped by countless cosmic events. Understanding the universe's origins also helps us glimpse its ultimate fate. The universe is still expanding, as Hubble first observed, and this expansion is accelerating. The mysterious force driving this acceleration is known as dark energy, a phenomenon that remains one of the greatest mysteries in modern physics. If the expansion continues unchecked, the universe may eventually face a big freeze, where galaxies drift so far apart that stars burn out, leaving the cosmos dark and cold. Yet, there is beauty in this cosmic cycle. The atoms that make up our bodies, our planet, and our universe will continue to exist, perhaps to form new stars, new planets, and even new life billions of years from now. As Krauss eloquently states, we are not only stardust, we are part of the universe's story. The discovery of exoplanets, galaxies, and the cosmic forces that shape them reminds us of our interconnectedness with the cosmos. Every step we take, every breath we draw, ties us to a universe that has been evolving for billions of years. As we search for another Earth, we are also seeking a deeper understanding of ourselves and our place in this vast and mysterious cosmos. Perhaps one day, we will find a pale blue dot orbiting a distant star, a world that mirrors our own. Until then, the story of the universe continues to unfold, reminding us of the incredible journey that brought us here and the infinite possibilities that lie ahead. As the universe cooled further, something remarkable occurred. The electrons, now moving at slower speeds, were able to combine with protons and neutrons to form the first stable atoms. This epoch is known as recombination, a pivotal moment in the history of the cosmos. For the first time, the universe became transparent, allowing light to travel freely through space. The photons released during this period make up what we now detect as the cosmic microwave background radiation (MBR), a faint glow that permeates the entire universe and serves as a snapshot of the cosmos in its infancy. The CMBR is the oldest light in the universe, a relic from when it was just 380,000 years old. When we study it today, using powerful telescopes like the Planck satellite, we are essentially looking back in time. Tiny fluctuations in the CMBR provide clues about the distribution of matter in the early universe, offering a glimpse into the seeds of galaxies and large-scale cosmic structures. These fluctuations were incredibly small, variations in temperature of only a few millionths of a degree, but they held the key to the formation of everything we see today. Over the next few 100 million years, the universe continued to expand and cool. Hydrogen and helium, the two simplest and most abundant elements, dominated this era, often referred to as the cosmic dark ages. There were no stars, no galaxies, and no light. Only vast clouds of gas spread thinly across an expanding universe. But within this darkness, gravity was quietly at work. Gravity began pulling the densest regions of gas together, forming clumps that grew larger and more massive over time. These clumps eventually became the first stars, marking the end of the cosmic dark ages and the dawn of a new era of light. These early stars, called population 3 stars, were unlike the stars we see today. They were enormous, hundreds of times the mass of our Sun, and burned at incredibly high temperatures. Because they formed from primordial hydrogen and helium, they lacked the heavier elements that give modern stars their complexity. These massive stars lived fast and died young, burning through their fuel in just a few million years before exploding as supernovae. These explosions released enormous amounts of energy, creating the first heavy elements like carbon, oxygen, and iron. The death of the first stars seeded the universe with these essential elements, enabling the formation of more complex stars, planets, and eventually life. As the universe evolved, galaxies began to form. These immense structures, composed of billions or even trillions of stars, became the building blocks of the cosmos. Galaxies themselves grouped into clusters and superclusters, connected by vast filaments of dark matter that form the cosmic web. A sprawling, interconnected structure that defines the large-scale shape of the universe. The Milky Way, our home galaxy, formed during this period of cosmic construction. Over billions of years, it grew by merging with smaller galaxies and accumulating gas and dust. In its center lies a supermassive black hole, millions of times the mass of the Sun, which influences the movement of stars and gas throughout the galaxy. Surrounding the Milky Way are countless stars, planets, and moons, along with mysterious dark matter that makes up most of the galaxy's mass, yet remains invisible and undetectable except through its gravitational effects. Within one of the Milky Way's spiral arms, about 4.6 billion years ago, our solar system began to take shape. It started as a dense cloud of gas and dust, which collapsed under gravity to form a spinning disk. At the center of this disk, a new star ignited, our Sun. Around it, smaller clumps of material collided and stuck together, forming the planets, moons, asteroids, and comets that make up the solar system today. Earth, our home, was one of these planets, forming in the Sun's habitable zone, the region where temperatures are just right for liquid water to exist. In its early years, Earth was a chaotic, molten world, bombarded by asteroids and comets. These impacts not only shaped the planet's surface, but also delivered water and organic molecules, setting the stage for life. The formation of Earth's atmosphere and oceans marked the beginning of a profound transformation. Simple, single-celled organisms appeared, harnessing energy from sunlight and chemical reactions to survive. Over billions of years, these microorganisms evolved into more complex life forms, eventually giving rise to plants, animals, and, much later, humans. As life flourished on Earth, the universe continued its slow march forward. Stars lived and died, galaxies collided and merged, and the expansion of the universe accelerated. This acceleration, driven by the mysterious force known as dark energy, remains one of the greatest puzzles in cosmology. Dark energy is believed to make up about 68% of the universe, with dark matter accounting for another 27%, leaving only 5% for the ordinary matter that makes up stars, planets, and everything we can see. Today, the universe is 13.8 billion years old and filled with wonders. From the vast beauty of the Milky Way to the distant galaxies billions of light years away, it is a testament to the power of natural processes. Every atom, every star, every galaxy is a product of cosmic evolution. A story that began with the Big Bang and continues to unfold. And yet, the story is far from over. The universe's ultimate fate remains uncertain. If dark energy continues to drive the expansion of space, galaxies will drift farther apart until the universe becomes a cold, dark, and empty place. A scenario known as the Big Freeze. Alternatively, if dark energy behaves differently than we expect, the universe could eventually collapse in a big crunch, reversing its expansion. Or perhaps dark energy could rip the cosmos apart in a dramatic big rip. Despite these uncertainties, one thing is clear. The universe is a place of constant change, driven by forces we are only beginning to understand. From its fiery beginnings to the formation of stars, galaxies, and life, the cosmos is a story of transformation, resilience, and discovery. As we gaze at the stars and study the faint echoes of the Big Bang, we are reminded of our deep connection to the universe. We are stardust, shaped by the same processes that created the galaxies and fueled the first stars. Our atoms, forged in the hearts of dying stars, are a testament to the remarkable journey that began billions of years ago. The universe's story is our story, written across the vast canvas of space and time. As we continue to explore, we uncover new chapters, each more extraordinary than the last. And with every discovery, we gain a deeper understanding of where we come from, where we are, and where we might be headed. A journey that will forever unite us with the cosmos. As the baby universe expanded and cooled, the tiny cracks in its otherwise uniform structure became crucial to its evolution. These imperfections, detected in the cosmic microwave background radiation, CMBR, by missions like WMAP, were the seeds of everything we see today. Galaxies, stars, planets, and even life itself. Without these small fluctuations in density, the universe would have remained a dull expanse of gas, devoid of the intricate structures that define it now. The material within these cracks was composed of swirling clouds of hydrogen and helium, the simplest and most abundant elements in the universe. Gravity began to work its magic, pulling the denser regions together. Over time, these regions grew more massive, attracting more gas and forming vast clumps. The voids between these clumps expanded, creating the cosmic web, a sprawling network of filaments connecting galaxies across billions of light years. These filaments, first glimpsed through simulations and later observed directly, revealed the large-scale structure of the universe, a breathtaking tapestry shaped by gravity. The next transformative moment in the universe's history came with the formation of the first stars. About 200 million years after the Big Bang, these dense clumps of gas reached critical mass. Gravity compressed them to the point where nuclear fusion ignited in their cores, creating the first sources of light since the CMBR. These early stars, known as population 3 stars, were unlike any stars we see today. They were massive, burning their fuel quickly and intensely, with lifespans of just a few million years. Composed almost entirely of hydrogen and helium, they lacked the heavier elements that make up modern stars. When these primordial stars died, they exploded as supernovae, scattering their enriched material across space. These supernovae created heavier elements like carbon, oxygen, and iron, the building blocks of planets, life, and even human bodies. Each supernova was like a cosmic alchemist, transforming the simplest elements into the complex ingredients necessary for the universe's next chapters. As the universe grew older, these enriched materials gave rise to the next generations of stars, which included more elements in their formation. Over billions of years, stars grouped into galaxies, and galaxies formed clusters, connected by the filaments of the cosmic web. One of these galaxies was the Milky Way, which would eventually become home to our solar system. The Milky Way itself formed through a process of mergers and accretion. Smaller galaxies collided and combined, their stars and gas clouds melding into a growing spiral structure. In its center, a supermassive black hole emerged, exerting a gravitational influence that shaped the galaxy's evolution. Surrounding it, billions of stars, along with planets, asteroids, and comets, formed a cosmic ecosystem. Among these stars was our Sun, which ignited around 4.6 billion years ago. The Sun was born from a dense cloud of gas and dust, part of a vast molecular cloud in one of the Milky Way's spiral arms. As the cloud collapsed under gravity, it spun faster, forming a disk around the young star. Within this protoplanetary disk, small particles of dust and ice collided and stuck together, gradually growing into planetesimals, early building blocks of planets. Over millions of years, these planetesimals coalesced into the planets, moons, and other objects that make up our solar system. Earth, the third planet from the Sun, formed within the Sun's habitable zone, where conditions allowed liquid water to exist. In its early years, Earth was a violent, molten world, bombarded by asteroids and comets. These impacts not only shaped the planet's surface, but also delivered water and organic molecules, the essential ingredients for life. As Earth cooled, its surface solidified, forming a thin crust. Volcanic activity released gases that created an atmosphere, and water vapor condensed to form oceans. These early oceans became the cradle of life. Simple microorganisms emerged, harnessing energy from sunlight and chemical reactions. Over billions of years, these tiny organisms evolved into more complex forms, eventually giving rise to plants, animals, and, much later, humans. While life flourished on Earth, the universe continued its slow march forward. Galaxies collided and merged. Stars lived and died. And new stars were born from the remnants of older ones. The expansion of the universe, driven by the mysterious force known as dark energy, accelerated. Dark energy, which makes up about 68% of the universe, remains one of the greatest enigmas in modern physics. Its influence ensures that galaxies are moving away from each other at an ever-increasing pace. The discovery of dark energy added a new layer of complexity to our understanding of the universe's fate. If its effects continue unabated, the universe could face a big freeze, where galaxies drift so far apart that stars exhaust their fuel, leaving the cosmos cold, dark, and lifeless. Alternatively, dark energy could trigger a big rip, tearing apart galaxies, stars, and even atoms. These scenarios remind us of the universe's impermanence and the delicate balance that sustains it. Despite these cosmic challenges, the story of the universe is one of resilience and creativity. From the tiniest quantum fluctuations in the CMBR to the majestic galaxies that fill the night sky. Every aspect of the cosmos is a testament to the power of natural processes. The imperfections in the early universe, detected by missions like WMAP and later confirmed by the Planck satellite, show us how these processes unfolded. The Planck satellite, launched in 2009, provided the most detailed map of the CMBR to date. By analyzing this ancient light, scientists gained unprecedented insights into the universe's age, composition, and structure. Planck revealed that the universe is 13.8 billion years old, composed primarily of dark energy, dark matter, and ordinary matter. It confirmed that the tiny cracks in the early universe became the galaxies, clusters, and superclusters we see today. One of the most profound implications of these discoveries is our connection to the cosmos. The hydrogen in our water, the calcium in our bones, and the iron in our blood were all forged in the cores of stars or during the explosive deaths of supernovae. As physicist Lawrence Krauss famously said, "We are stardust." This realization underscores the intimate relationship between humanity and the universe. Our journey to understand the universe is far from over. Telescopes like the James Webb Space Telescope promise to unveil new secrets about the first galaxies and stars, while projects like the Euclid mission aim to unravel the mysteries of dark energy and dark matter. As we peer deeper into space and time, we uncover new chapters in the cosmic story. From the faint glow of the CMBR to the brilliant light of distant galaxies, the universe is a constant source of wonder. Its story, spanning billions of years, is a tale of creation, destruction, and renewal. A journey from simplicity to complexity, from chaos to order. As we explore the cosmos, we not only learn about the universe's origins, but also gain insight into our own place within it. The universe began as a tiny, hot fireball, a moment of pure energy. From that singular event emerged everything we see today: galaxies, stars, planets, and life. And as we look to the future, we carry with us the knowledge that we are part of this vast and extraordinary story. A story that continues to unfold, connecting us to the cosmos in ways we are only beginning to understand. Hubble's discoveries redefined our understanding of the universe. The Hubble Deep Field Image was more than a snapshot. It was a time machine, revealing galaxies from 1 billion years after the Big Bang. These faint smudges of light told a story of transformation, of stars creating the heavier elements that would eventually become the building blocks of planets, life, and everything we see today. By analyzing the spectra of these distant galaxies, scientists confirmed that the early universe had already started producing elements beyond hydrogen and helium. These included carbon, oxygen, and nitrogen, essential ingredients for life. This confirmed Fred Hoyle's groundbreaking theory that stars acted as cosmic forges, creating heavier elements through nuclear fusion. Hoyle's idea of stars as factories of matter became a cornerstone of modern astrophysics. The process begins deep within a star's core. Under immense pressure and heat, hydrogen atoms fuse to form helium, releasing vast amounts of energy, a process that powers stars like our Sun. As the star ages and its core temperature increases, helium fuses into heavier elements like carbon and oxygen. In the most massive stars, this chain of fusion reactions continues, creating elements as heavy as iron. But iron marks the end of the road. Fusion can no longer provide the energy needed to counteract gravity, and the star collapses. For the most massive stars, this collapse triggers a supernova, a violent explosion that scatters the star's material across the cosmos. It is during these explosions that even heavier elements like gold, platinum, and uranium are formed. Every atom of gold in your jewelry and every molecule of oxygen you breathe was forged in the heart of a dying star. These stellar explosions seeded the universe with the elements necessary for the formation of new stars, planets, and eventually, life. The material ejected by one generation of stars becomes the raw material for the next. This cycle of creation and destruction continues to shape the universe, making it richer and more complex with each iteration. Hubble's images of star-forming regions, like the pillars of creation in the Eagle Nebula, captured this process in breathtaking detail. These towering columns of gas and dust are interstellar nurseries, where gravity pulls material together to form new stars. Within these dense regions, stars ignite and begin their nuclear fusion, lighting up the nebula with their brilliance. These newly born stars, in turn, shape their surroundings, blowing away gas and dust with powerful stellar winds and creating space for the next generation of stars. In some cases, the leftover material around a newly formed star condenses into disks where planets take shape. This process mirrors the formation of our own solar system, where a protoplanetary disk surrounding the young Sun gave birth to Earth and its neighboring planets. Hubble's ability to peer into these nurseries offers us a glimpse of how planetary systems like ours come into existence. The successes of the Hubble Space Telescope were hard-earned, but its legacy is unparalleled. Its images transformed our understanding of the cosmos, not just by showing us where we came from, but by inspiring questions about what lies beyond. Hubble's observations paved the way for the next generation of telescopes, such as the James Webb Space Telescope, JWST, launched in 2021. JWST builds on Hubble's legacy by pushing the boundaries even further. With its powerful infrared capabilities, it can peer through dense clouds of gas and dust to study the earliest galaxies and star-forming regions in unprecedented detail. Where Hubble saw the first galaxies, JWST aims to see the very first stars, shedding light on the universe's darkest epochs. It will also search for signs of life on exoplanets by analyzing their atmospheres for chemical fingerprints of water, oxygen, and other molecules associated with life. Hubble's revelations, combined with data from missions like JWST, remind us that the universe is a place of constant change and creativity. Every image, from the pillars of creation to the Hubble Deep Field, tells a story of how the cosmos evolves over billions of years. The light captured by these telescopes allows us to witness events that happened long before Earth even existed. But these discoveries also raise profound questions. Are we alone? Is there another world out there, orbiting a distant star, where life has taken root? Hubble's observations of exoplanets and JWST's ability to analyze their atmospheres bring us closer to answering these questions. By studying how stars create the elements needed for life and how planets form in their wake, we gain insight into the conditions that might make life possible elsewhere. As we look at the spectacular images captured by Hubble, it's impossible not to feel a sense of wonder. The stars, galaxies, and nebulae it reveals are not just distant objects. They are part of our story. The atoms in our bodies were forged in the fiery cores of stars. The water we drink contains hydrogen created in the Big Bang. Even the gold in our jewelry came from the cataclysmic deaths of ancient stars. Fred Hoyle's insight into stellar nucleosynthesis and Hubble's exploration of the cosmos have deepened our understanding of this connection. They remind us that we are not separate from the universe, but an integral part of it. We are made of star stuff, shaped by the same processes that govern the galaxies and nebulae we see in Hubble's images. The discoveries of the Hubble Space Telescope mark a milestone in humanity's journey to understand the cosmos. But they are not the end of the story. With JWST and other next-generation telescopes, we are poised to uncover even more about the universe's origins, evolution, and future. From the first stars to the birth of new worlds, the universe is a story of transformation, a story we are privileged to witness. As we continue to explore, we are reminded of the words of Carl Sagan: "We are a way for the cosmos to know itself." Through the lens of telescopes like Hubble, we glimpse the vastness of the universe and our place within it. And with every new discovery, we take another step in understanding the profound connection between ourselves and the stars. Thank you for watching. Don't forget to like, subscribe, and share your thoughts in the comments below. Until next time, keep exploring.